Okay class, so today we got a request to do problem 4.20 from chapter 4, and this problem wants us to find two things: the node voltages at V1, V2, and V3, as well as the total power dissipated in the circuit. Since we want to know the node voltages, it's probably best to start this problem by looking at using the node voltage method. So I want to minimize this and look at it in Paint so I can write a little bit more easily. But here we have nodes 1, 2, and 3. And so if we want to do the node voltage method, the first thing we do is we use Kirchhoff's current law at each node. So if I look at node 1, so I'm going to do KCL, or Kirchhoff's current law, at node 1. Okay, so here we have a 5 IO, because this is a dependent source current coming into node 1. So our standard convention is going to make that negative. So I'm going to say negative 5 IO. And then this resistance, we're going to assume that the current coming out of node 1, since we have a positive differential here, is going to come in this direction, right? This one, I don't really know what the difference between node 1 and node 2 is going to be, so I'll assume it's coming out there. And then again, on this one, I'm going to assume the current is coming down because I say I have a positive voltage differential across that. This one, again, not sure, so just for consistency, I'm going to assume it's going down to the right. And this is going to make things a little bit easier for me moving forward, right? And I'm not going to bother labeling all of these IOs because I'm going to replace them with the voltage terms anyways here. Okay, so continuing to write this equation for the current coming out of the 20 ohm resistor here, right? We're going to say that's coming out, so it's going to be positive. So we'll say plus. And then we have V1. And again, the reference that we're going to put is at the bottom here. So that's going to be 0, right? So we have V1 minus 0. I'm not going to bother writing the minus 0. Over the resistance, 20. And again, this quantity here describes the current coming out of node 1 along this branch right here, right? And then, again, we have another current coming out, so I'm going to say plus. And then here we're going to have the difference between voltage V1 and V2. And I'm assuming that V1 is having a higher voltage in this case because that's the direction under the current. So I'm going to say V1 minus V2. That's the voltage difference divided by the resistance of 5 ohms. And then this whole thing should be equal to 0, right? So in this we have 3 terms in one equation, so we know we can't solve this right away. So let's go ahead and take a look at our node 2. In this case, we have our current coming in, so we're going to say V1 minus V2 over 5. And again, that's the same as the current that we saw from this branch right here, but now it's coming into the node, so I'm going to say this whole thing is negative. And then we have the current coming out of node 2 going towards ground through the 40 ohm resistor. So I'm going to say that's going out of the node. So I'll say plus V2. And again, I could write minus 0 on this, but I'm just going to save space on my pad. So divided by our resistance, which is 40 ohms. Right? So that's the current leaving node 2 going towards ground. And then we have the current leaving node 2 going towards node 3. So again, since it's leaving the node, I'm going to say plus. And then we have our V2, again assuming that V2 is larger than V3, minus V3 divided by our resistance, which is 10 ohms. And again, we're going to set that equal to 0, right? Alright, so now we have 2 equations, and now we have 4 unknowns. We still can't solve this. So let's write our third equation for our node here. And again, we can note just as a reference for when we start to write this, that this is going to be 96 volts at this location, since we know that the only thing we have here is this 96 voltage source, right? So that helps us a little bit. So if we write, oh sorry, I forgot to write, this is, equation right here is Kirchhoff's current law at node 2. And then we can can do Kirchhoff's current law at node 3. Right. So node 3, again, we have the same last term, but it's coming into the node. So I'm saying negative V2 minus V3 over 10. That's the current coming into node 3 from the left. Then I'm going to say plus. Now here, I don't have node voltage defined right here, right? So I don't know what this voltage between the ground and the resistor is. And so if I want the current going through here as a function of my voltage, right, I got to define what the current at this resistor is, right? So I'm going to call this, just as a temporary holder, V4, right? And I know that V4 is going to be equal to 11.5 IO, right? Because that is the dependent voltage source, right? So here we can say that this is our dependent voltage source, and we know that V4 is equal to 11.5 IO because it's the only thing between that and ground. All right, so I'm going to write this replacing V4 with that 11.5 IO, right? So this will be, oh, let me change back to black. So if we say here, we're going to say plus because this is leaving. We're going to say V3, well, it would be minus V4, but again, I'm going to replace that with our 11.5 IO, right? And this whole thing divided by 5 ohms, right? Because this is the current that's going to be going through this 5 ohm resistor, right? Which is what we're writing for basically all of these terms. And then I'm going to say plus, and probably this is going to work out to not be true, but I'm still assuming that V3 is higher than our 96 volt because that's the way I drew the current, right? And it's not a problem doing it this way. We'll just get negative values for some of these. And since we don't know what the voltages are anyways, you know, it doesn't make too much difference. So we're going to say V3, our 96 minus our 96 volts, divided by our resistance on that branch, which is 4 ohms, equals to 0. And we're losing a little bit of the screen here, but that's not a big deal, so equals to 0. Now, we have 3 equations, and we actually have 4 unknowns, because in our first equation here, we have IO, right? So you may say, oh, in this equation down here, we also have IO. You may say, well, Dr. Lura, no, we can't solve this, right? We have 3 equations and 4 unknowns. But we know that the current IO, right, is equal to the current coming through this branch, right, which we've defined a couple of times in this equation. It's just this V2 over 40 term, right? So if I say that IO is equal to V2 minus 0, right, over 40, that's our current IO, right? So every time I see IO, I can replace that with my V2 over 40. So this equation is going to become, I'm just going to write over in a different color, V2 over 40, right? So 5 times V2 over 40, not 40, that's a little bit bad, let's try and do that. 40, right? And then down here, I can write this. Again, I can just cross that out, and I can say this is V2 over 40, right? Now we got to collect all of our terms and rewrite this. Now we have 3 equations and 3 unknowns, so we can solve this, right? So for our first equation, so I'm going to write this for equation 1. I want to write these out, so I have V1 times some constant plus V2 times some constant plus V3 times some constant equals some independent term, right? I'll do the same thing for equations 2 and 3, right? So I need to collect all of the coefficients for this, right? So on this first one here, I have 1/20th, which is positive 1/20th, and positive 1/5, right? So V1 is going to be 1/20th plus 1/5. And if you trust the math that you can do in your head, right, you could obviously say, well, 1/5 is 4/20ths, that ends up being 5/20ths, or, whatever you want to do. But if you just write it out here and plug it in your calculator, you don't trust your mental math, you can do that and your calculator shouldn't make any mistakes. Hopefully, you type things in right? And then for our V2 terms, we have 5/40ths, right? And that's negative. And I know that 5/40ths is the same as 1/8, because if I divide 40 by 5, I get 8. So I'm going to write this as negative 1/8 V2, right? And then I also have a negative 1/5. So I'm going to say 1/8 minus 1/5, right? V2. And then I don't have any V3 terms on here, so this coefficient is going to be 0, right? And I also don't have any independent terms, so the independent terms here is also going to be 0, right? And if I wanted to solve this equation by hand rather than plugging it into a calculator, I could use this first term and substitute it into the other two equations to get two equations, two unknowns, and then do the same those two equations. But once I've already written it out like this, it's probably easier just to go ahead and do it in your calculator and let your calculator give you the answers, right? All right, so our second term for V1, we have negative 1/5 V1, and that's the only term we have there for V1, so I'm going to say negative 1/5 V1, right? And then plus, what terms do we have for V2? So we have a negative times a negative, so we have a positive 1/5, so 1/5. And then we have V2/40, right? So we're going to say plus 1/40th. And then we have it V2/10, so we're going to say plus 1/10 V2, right? And then I'm going to say, okay, we have our V3 terms. The only thing we have here is we have a positive, negative 1/10. So I'm saying negative 1/10 V3. And it's always a good idea to make sure you have all these terms kind of written out correctly for each one. So I have 3 V2 terms because 1, 2, 3 V2, 1, 2, 3 V2. I have 1 V1 and 1 V3, and I don't have any independent terms. So I'm going to say that equals to 0. And then our last one here, we actually don't have any V1 terms, right? We only have V2 and V3. So I'm going to say 0 V1. And then on V2, we have a negative 10th here. So I'm going to say plus. I'm going to put the negative terms. I don't know if they're all going to be negative or not. So I'll say plus negative 1/10, right? And then we have a 11.5 over 40/5, right? Which is a little bit confusing, but we can just write this as minus 11.5 divided by 40 times 5, right? And try to make sure that this is a decimal and this is a multiplication. I don't know if you want to make that obvious because that could be pretty confusing. Again, that's the V2 term, right? And then this one doesn't have any V2 terms, so I'm going to go ahead and close off that bracket, right? V2. And then, so that's our 2 V2 terms, and then we have 3 V3 terms, and we have a negative and a negative, that's a positive. So I say plus 1/10, right, of our V3. And here we have plus 1/5, so I'm going to say plus 1/5. And then I'm going to look and say, okay, here we have plus 1/4, so plus 1/4, right? And then those are my 3 V3 terms. So I have 2 V2 terms and 3 V3 terms, so I've at least kept track of all the terms. Hopefully I kept track of all the appropriate signs and everything. We have negatives on our V2s, which looks right, and we have positives all on our V3s, which looks okay. So if I'm being careful here, that should be good. And then here I have a negative 96/4, If I move that to the opposite side of the equation, it's going to be positive, so 96 over 4, right? Now you can set this up in your calculators. I'm just going to do it in MATLAB real quick because it's hard for me to do a screen capture on my calculator. But it works pretty much the same. So give me just a second for this to load. Alright, so I've got MATLAB loaded up here. And so the first thing I'm going to do is I'm going to define my coefficient matrix. I'm just going to call this C. And this is the matrix of all the coefficients for V1, V2, V3. So I'm going to say C is equal to the matrix, and I have the first term here is 1 over 20 plus 1 over 5. And again, it's going to do the division before the addition, so the order of operations there should be fine. The second column of the first row, we have negative 1 over 8 minus 1 over 5. And then the last one here, we have 0. I'm going to use a semicolon to specify a new row in that matrix. Go down to the next one. I'm just doing this to try and make it look a little bit nicer. You don't actually have to go to a new line if you don't want to. And then for my V1 term here, I have negative 1/5. And then for my V2 terms, I have 1/5 plus 1/40 plus 1/10. And then for my V3 terms, I have negative 1/10. Again, I'll go to a new row. New row. And then we have 0 for V1. And I have negative 1/10 minus 11.5 divided by 40 times 5. On this one, since it does multiplication and multiplication on the same step of operations, I want to make sure I do 40 times 5 in the denominator in parentheses, so it knows to do that multiplication before it does the division. So be explicit on that. And then that's the end of our V2 term for that equation. And then for V3, I'm sorry, I made a little typo here. This should be V3. Right, it should be our V3 down here. So I'll just fix that real quick and then come back to MATLAB. So for V3, we should have our 1/10. Let's put these in parentheses. 1/10 plus 1/5 plus 1/4. And so that should be the end of our matrix. So let's define that. There's the decimal values for each of those, right? And then we need to define our independent terms. And again, I need this to be a column vector, so this is going to be 0, and then a new row, 0, then a new row, and then 96 divided by 4. Right, once we've got that, not suppress the output on that, right? And then we need to do the inverse of C, so I'm going to do C to the negative 1, and then that quantity times I. And so we get our voltages. V1 is equal to 156, and V2 is equal to 120, and V3 equal to 78. So I'm going to just take a break real quick and pull up the solutions and check and see, make sure that's right before we continue on. So let's take a look at this. We can see that we have 156 for V1, 120 for V2, and 78 for V3. So assuming that these are in the same order, which I think is probably a good assumption, right? We have the correct voltages. So I'm going to go ahead and go back to my notepad down here, and I'll write those out. So we know that we have V1 equal to 156 volts. Ooh, that's a really bad V. Volts. V2 equal to 120 volts, and V3 equal to 78 volts, right? So that's part A. All of this is part A from the problem. And part B from the problem wanted us to find the total power dissipated in the circuit, right? And to do that, there's two ways of going through that. We can find the current going through and the voltage across each of our sources, figure out the total power generated, right? Or we can figure out the current going through each of our resistors and figure out what the total power dissipated is, right? I guess we have to figure out whether or not the sources are going to be positive or negative anyway, so it's probably easier for us to figure out what the total power dissipated in the circuit is by looking at each of our sources, right? So in this case, we know that we have power is equal to voltage times current, right? So P is equal to IV, right? And we say that power dissipated is positive, right? So if we have power current going from positive to negative, we're actually dissipating power, and this is the positive convention, right? So we have three sources on here. So if I look at these sources and I know whether or not they're generating or dissipating power, that's going to be faster than looking at the 1, 2, 3, 4, 5, 6 resistors that we have here, right? We also know that our V4, right, is equal to 11.5 I/O. So our V4 here, and we know that our I/O is going to be equal to our V2 divided by 40, right? So let's say I/O is equal to our V2, which is 120, divided by 40, and this should give us 3 amps, right? This is 120 volts and 40 ohms, so this would give us units of amps. Again, if this was kilo ohms or something else, then we would have to do the appropriate conversion for that. And if it was kilo ohms, then we would get milliamps instead of amps, right? So we have our I/O is equal to 3 amps, right? So if this is 5 I/O, that means that this current here is actually going to be, I'm going to call this source 1. I'll call this source 2 and source 3, just to be a little bit faster here. So this source is going to have a current of 15 amps. And we know this is going from negative to positive voltage. I'm not going to bother switching the colors here because it's the same as our voltage V1, right? So the power in our source 1, let's see, power source 1, right? We have 15 amps, and we have V1 volts, which is 156, and 156 volts. And since we're going from negative to positive, again, this is our opposite of our convention, so this is actually going to be a negative or a generated power, right? So this is generating power, right? And so we can calculate this out. 15 times 156. I'm just going to go back to Excel or to MATLAB real quick and calculate that. So we have 15 times 156. So that'll be 2,340 watts of power. So, I'm going to move this side so I can still read it. 2340. So, negative 2,340 watts.
I didn't know you're in radio now.
So now we have to find the power in our other two sources, right? So let's go ahead and take a look at our dependent voltage source. We know the current through this is going to be the same as the current coming from the branch 3 down through 5, right? And we know that our V4 is 11.5 I/O. Again, we define I/O as 3 amps. So our V4 is equal to 11.5 times 3, right? So we're going to have 34.5 volts. And again, we just assume that the units of this are volt amps, right? Just because otherwise it doesn't really work on this problem, right? So we know that's our V4, and so if we have our V3 is 78 and our V4 is 35, we can calculate the current going through our second source. So I'm going to say, I'll just call this, what do you want to call it? Let's call it I5, because it's going through the 5 ohm resistor, because why not? So our I5 is going to be equal to our V3, which is 78, minus our V4, which was our 34.5, divided by our resistance, which is 5 ohms. Again, this is voltage over ohms, so we should get amps. And so let's calculate that out real quick. 38 minus 34.5, that whole quantity, divided by 5. I'm just doing this in MATLAB just off screen. We calculate that, we should get 8.7 amps. So here we get 8.7 amps, right? And then we know that the current in this case for the power in our source 2, so power source 2, current is actually going from positive to negative, right? Because it's going down the potential difference. So because that's the case, this is actually going to be dissipating power. So I'm going to say the power from my source 2 is going to be a positive, right? And it's going to be our current 8.7 times our voltage. Again, this is amps times volts, so we're going to get units of watts. Our voltage of 34.5. And so if we do that math real quick, 8.7 times 34.5, we get 300.15. So 300.15 watts. So 3, if we wanted to round here, then that probably wouldn't be a terrible idea, but 300.15 watts. And I'm just going to consider this 300 watts, because that seems like an unnecessarily high level of precision, trying to go to 5 significant figures. So, all right, and then for our last source here, we got to figure out the current going through our 4 ohm resistor. So let's just call this our I4, because we haven't used that, and it's also the 4 ohm resistor. And we know that our I4 is equal to this term right here, right? Our V3 minus 96 over 4. So our V3, I4, is equal to V3, which is 78, right? Minus 96 over 4, right? Which this just means that we assumed that that current was going in the wrong direction, right? So it's actually going to be we're going to get a negative current. So if we calculate that out, I'll move this to the screen so you guys can see it. 78 minus 96, that whole quantity, divided by 4. So we get negative 4.5 amps. Okay, so in here, negative 4.5 amps, right? So that current is actually going in the opposite direction, right? And then on our source here, we can see that the way we've drawn it is going from positive to negative, so we would assume that it is producing power, but since we have a negative value, it's going to be a double negative. So we'll get, well, a positive and a negative, so we'll end up getting a negative power, or we're going to end up being dissipating power, right? So if we keep this assumption that the current is going this way and leave it negative, or we change the direction and change this to positive. I'm going to keep the convention that I drew on here, right? So for my power source 3, power at source 3, I'm saying that the current is going from positive to negative, right? Which would be a positive power, right? Then I have a negative current, 4.5, right? The only thing you don't want to do is you don't want to use the way you've drawn it and then not use the negative, right? Or use the positive and then use what you've drawn it. You got to account for that one way or the other, not both ways, or you end up having a double negative. Times our voltage, which is 96 volts. And so we're going to get a power here, 96 times 4.5. I guess I'll move this so you guys can see it. So 432 negative, again, negative 432 watts, right? And so our total power used by the system, right, the power generated has to be equal to the power dissipated. So this one is dissipating power, these two are generating power, so the other resistors are dissipating the difference here. So I only need to count for the ones here, right, that are generating power. Some people may make this think of taking the sum of all of these, but we're not calculating the power dissipated by the resistors. We know that the resistors are going to be dissipating however much power they need to make the total power equal to 0, right? So I'm just going to take these two terms. So I have 2,340 and 432. So let's do that. So 432 plus 2,340. So we get 2,772 watts. So total power, let's do it in the corner here. Total power generated is equal to 2,772 watts, right? And the total power dissipated would be the same number, right? I would have to do this 300 watts plus all of my resistors to figure out what the total power being lost was. But since resistors can't generate power, I think this is a little bit easier. And again, we should probably check that relative to the solution. Let me see here that we get 2,772. So, yay, we didn't make any math errors. Hope that made sense to everybody. If not, feel free to let me know, and I will try and post some clarification if there's some kind of issue. Thanks for watching.